So I'd of course like to begin by thanking the organizers for this opportunity to present my work. The work itself is something we have been confused about for many years now, starting about 2015, and it finally resolved itself recently. And so that's why I'm quite excited to talk about it. Much of what I'm going to show you is the work of my present graduate student, Ritesh Bhola, and a previous graduate student who kind of started this just before he graduated. And Mursaling Islam is another student who played a crucial role. And this goes back to the thesis work of Sambuddha Sanyal some 7-8 years ago, and even earlier to the thesis work of Lessig Mortonuk, who worked with me 20 years ago on similar things. So let me, of course, also add that I'm particularly excited because it's an opportunity to felicitate Deepak and Mustansir, who have played and continue to play such an important role in our community. And I hope this will continue to be the case for many more years to come. So since I'm the first speaker in this session on percolation, I thought let me begin with a few generalities, which although they are well known, are worth repeating perhaps once. So we know that quench disorder, impurities that don't move on the time scale of the experiment, are very important in many contexts in condensed matter physics. So for example, particles scatter and diffuse maybe sometimes anomalously when they have to deal with impurity potentials. And we know that matter waves can scatter and do something even more interesting, which I'll come to in a minute. The simplest setting to study this, of course, is a porous random medium and classical transport of a particle fluid. And it's simple because it's the random geometry of the medium that then completely determines the fluid transport to a first approximation. And this leads to the paradigm of percolation, which was introduced by Brodmann and Hammersley many years ago. And more generally, one can talk about the diffusion in the presence of additional random potentials apart from the constraints of the geometry. And that is, there are many variants of this. So what is percolation? It's simply the question, can you study the end-to-end connectivity of a porous medium and say something sharp? So the question you ask is, you have a porous medium, can you go from one end to the other along the allowed paths in that medium? And the thing that makes this interesting is that the answer changes in a very dramatic way as a function of porosity. And this dramatic change can be captured by simple models. And the simplest model is, of course, a randomly diluted regular lattice, like a graph. And this is the beginning of the subject in the 50s. And the particular question that is simplest to describe is the crossing probability. So consider, for example, a two-dimensional square grid or a cubic lattice of some linear size L, and you remove some fraction n back of sites or delete links of that fraction. And PW then is the probability that I can walk from one end of that sample to the other end of the sample along the existing sites and links. And the question is, how does this probability behave as a function of the dilution probability, the dilution and the size of the system? And what's really interesting is that there's a sharp threshold behavior. In the thermodynamic limit, the answer goes from 0 to 1. And this is the percolation transition. And this is the simplest geometric example of a thermodynamic phase transition. And the approach to the thermodynamic limit, the L going to infinity limit, is of course also very interesting because this probability collapses into a universal dimensionless function of a dimensionless scaling variable, which is the deviation from the critical dilution times the system size to some power, which is 1 over the correlation length exponent. And this is the phenomenology we know and love from thermodynamic phase transitions. And it's particularly nice that it appears in this extremely simple geometric problem, which you could explain even to a high school student. Let me now sort of begin with my talk proper. If you talk about matter waves, not particles, then of course there's also the phenomenon of Anderson localization, which comes about because waves can interfere with themselves. And that's a whole subject in its own right. And the simplest model in which one might want to study something like Anderson localization is, of course, the disordered tight binding model. So psi is the wave function defined on sites of some random lattice. Tijs are the hopping amplitudes between allowed links of the lattice, and Vi's are the random potentials. And so this is, if you will wish, a question about the character of the wave functions of this random matrix Tij plus Bi delta Ij. Uh, there is a particularly simple case you can think about, which is the analog of the percolation problem, which is the problem of vacancy disorder. So you don't have random potentials, but some orbitals in this tight binding model are missing. And this is natural, for example, if substitutional impurities correspond to a missing orbital, like in a binary alloy. And this leads me to sort of the closest point of contact between Anderson localization on the one hand and percolation on the other hand, which goes by the name of quantum percolation, introduced by Kirkpatrick and Agata some 50 years ago to describe the behavior of binary alloys. So you have vacancy disorder, no external random potentials. And the question you're now asking is, at a given Fermi energy, can the quantum electron fluid be localized even when the corresponding classical fluid can diffuse or percolate from one end to the other? So the underlying lattice is above the percolation threshold. You can go from one end to the other in the thermodynamic limit, but can the electron fluid still be localized because of interference effects? That's the question that they tried to ask in the context of binary alloys. And the simplest example of this question is for bipartite random hopping problems on a diluted bipartite lattice. So I've added an extra structure to this, which is the bipartiteness, which simplifies things. And this was the case they considered originally anyway. So when the lattice is bipartite, the hopping Hamiltonian, the tight binding model, has a spectrum which is symmetric about zero energy. Zero is special because a state with energy epsilon will always have a partner at minus epsilon. This symmetry is broken by random potentials and by next nearest neighbor hopping, but in the simplest case, you have this extra symmetry. So the question then arises, does vacancy disorder change anything near zero energy because zero is special? And the answer, well, at first sight, surprising answer, at least it surprised us until we started thinking about it, is that whenever you have non-zero dilution in the thermodynamic limit, for a large enough lattice, almost every sample will have zero modes. In fact, the probability of having at least a zero mode goes to 1 in the thermodynamic limit at any non-zero dilution. That's what's being shown here. F is the probability of having at least one zero mode. And in fact, there's a non-zero density of zero modes in the thermodynamic limit. This is the non-zero density of zero modes on the y-axis. The x-axis 1 over L. And this is just to show you that we have reached the thermodynamic limit. We have these flat lines. And so when we encountered this first in the problem of diluted graphene, we started wondering where they come from. And then we realized the answer is actually quite straightforward. At least we thought it's straightforward. So our idea was that they are coming from regions of the lattice with local sublattice imbalance. So for example, and a particular structure of the boundary. So let me spend a minute on this slide. Look at the picture on the left. Here's a region where locally the number of B sublattice sites is bigger than the number of A sublattice sites. Yet the boundary of this region is all of the minority, locally minority sublattice, which is the A sublattice. So if you have such a region in the lattice, you can just by constraint counting convince yourself that there will be NB minus NA, which is what I'm calling IB, the imbalance, number of zero modes in this region of that tight binding model, right? And these modes exist simply because the number of variables is more than the number of equations that they have to satisfy for the zero energy Schrodinger equation. And the amount they're more by is exactly this imbalance, and that's the number of linearly independent solutions you will have. So our idea was that, you know, there are rare fluctuations in the geometry of this diluted lattice that produce regions like this, and they host these modes. So fine, I mean, is this true? I mean, does this really happen? These were the questions. So we first started cooking up simple pictures, simple examples of such regions. And here's an example with 6 vacancies, which are denoted by the red dots on a honeycomb lattice. And I've just drawn the wave function for the particular case where some of the hopping amplitudes are -1 and some are +1. The blue are supposed to be -1, these are supposed to be +1. The point of doing that is to emphasize that these modes exist independent of the specific values of the Tij. In that sense, they are topologically robust because they only care about the geometry. they only care about the topology of the lattice and not the details of the hopping amplitude, magnitudes, and signs. And just drawing a picture like this gives you a rigorous lower bound on the density of zero modes on the honeycomb lattice. But when we went ahead and looked more carefully numerically, we found that the number of actual zero modes is way larger than this lower bound. So what dominates? This was the next question. Is there a general algorithm for identifying all these rare regions, assuming that all these things come from such regions, which I call R-type regions? Can I come up with a maximally localized basis for the zero mode subspace? And then if I can, then can I use that to come up with some basis invariant consequences for the zero energy Green's function so that I can answer that original question about whether a quantum fluid can percolate when a classical fluid does. Right. So our approach was to realize that these modes are disorder robust in the sense they don't depend, their existence doesn't depend on Tij's exact pattern, only depends on the connectivity, not the hopping strengths. And they, in our, at least our conjecture was they rely on a local imbalance between A and B type site densities. And so that immediately led us to think in terms of matchings or dimer covers, because after all, a dimer on a lattice matches an A site with an immediate nearest neighbor B site. So wherever you cannot put dimers, a perfect dimer cover, that's where there's local sublattice imbalance.
Professor Damle, you have got 2 more minutes.
Yes. So this was a good idea, and it turned out that this is well known. Longuet-Higgins, in a completely different context, had understood that the number of monomers in any maximum matching of a bipartite graphs gives the number of topologically protected zero modes. But what was not clear is what was the wave function to look like, and what is there a sort of a maximally localized basis. And this is where we sort of made our Greek progress. We brought into play a classic result from graph theory called the Dulmage-Mendelssohn decomposition, which allowed us to come up with a systematic procedure for constructing all these R-type regions that can host monomers and therefore zero modes. And since I have another, so our computational strategy then was to use some well-known graph theoretic algorithms to compute this Dulmage-Mendelssohn decomposition, from it identify the R-type regions, and then look at their geometry, their random geometry, because that's where the zero modes live. And I think pictures can often say much more than I can. So here's a picture of R-type, the 3 biggest R-type regions in a honeycomb lattice of some 3000 by 3000 size at about 5% dilution. And you can see they're huge. This entire blue mass is one R-type region. So they get very big at low dilution. And to cut a long story short, we have very clear evidence that the probability that you can go from one end of the sample to the other in an R-type region climbs to 1 in the zero dilution limit in a very specific way, which obeys a scaling law, suggesting incipient percolation at zero dilution with a critical exponent nu of 5.1 roughly. And in 3 dimensions on the cubic lattice, we get a percolation transition, a sharply defined second order percolation transition at a non-zero vacancy density. And a second transition that corresponds to a spontaneous breaking of sublattice symmetry. And as a consequence, we can establish that there is no quantum percolation transition in the bipartite case in 2 dimensions. And in the 3 dimensions, this transition is basically governed by the Dulmage-Mendelssohn percolation in the 3-dimensional lattice. I think I should stop here and put up my acknowledgement slide. Thank you.
Thank you, Professor Damle, for the very interesting talk. The floor is now open for questions. You may unmute yourself and ask the questions.
Hi, Kedar.
Hi.
So, what happens on, let's say, if I take a random bipartite graph?
Yeah, so that's something we're working on right now, actually. One has to be a little careful because you have to define what you exactly mean by a random bipartite graph. If you're talking of a bipartite version of the Erdős-Renyi graph, then that's a bit weird, right? So there are other ways of doing this, and we suspect there is a Dulmage-Mendelssohn transition on that graph as well. We haven't been able to characterize it analytically, but we are looking at it numerically.
Okay, thanks.
Are there any further questions?
Yeah. Yeah, hi, Kedar. So,
Hi.
so I didn't. I'm not sure I understood clearly. I mean, so does this R region sort of form a percolating cluster now?
That's the idea. So in
Okay.
3 dimensions, it's very clear. These R-type regions in the 3-dimensional case percolate at a particular value of dilution. And the evidence for that is this crossing. This is the probability that I can walk from one end of the cubic lattice to the other in the thermodynamic limit, or in the limit of a large size, through a single R-type region. And so you can see I go from sizes which are 500 cube to 1100 cube, and I get a clean crossing point. And this is the Dulmage-Mendelssohn percolation transition in 3 dimensions, with a nu that we can extract. It's around 1. And in 2 dimensions, something more interesting is happening. There isn't really a non-zero dilution critical point, but the size of these regions grows as you decrease your dilution. They get bigger and bigger and bigger, and they get bigger and bigger and bigger in a way that satisfies scaling. And that is the statement that if you look at the probability to go from one end of the sample to the other in 2 dimensions through a single R-type region, that probability scales with this kind of scaling form. So instead of saying NVAC minus NVAC critical, you just have NVAC. So it's a zero dilution critical point, which is a little confusing, but there's an order of limits involved. What we are really saying is that if you take the thermodynamic limit at any non-zero dilution, then the R-type regions are localized, but their size is now growing and becoming infinity is a power law in NVAC as NVAC goes to 0. So it's incipient percolation in 2 dimensions and just regular percolation in 3 dimensions. And from the percolation point of view in 3 dimensions, there's something very interesting. Just below the percolation transition in 3 dimensions, there are 2 infinite clusters. I mean, two very large clusters, one A type, one B type. And then there is a second transition at which spontaneously in each sample, either the A type grows at the expense of the B type or vice versa, and now there's a single cluster. And this is a spontaneous breaking of sublattice symmetry inside the percolated phase. So you go from 2 infinite clusters to 1 infinite cluster inside the percolate. That's a second transition, which is a spontaneous breaking of sublattice symmetry.
Thanks.
Any more questions? Okay, if there are no further questions, let's take this moment to thank Professor Damle for such a very interesting talk.